Hello. When you add all the terms of an infinite sequence, you get an infinite series, and it's denoted with the Greek letter sigma. The bottom index tells you what value of n to start with. The top of the sigma tells you where to end if you're supposed to end. An infinite series, you will see an infinity up here. If you're only supposed to add like the first 5 terms, then your index will start at 1, and then your ends will increase until you hit 5. Consider an infinite series 1 over 2 to the n power. If we start plugging in positive integers, 1, we get 1 over 2 to the first, which is a half. 1 over 2 squared, that's 1/4. 1 over 2 cubed, that's 1/8, and so forth. 1 over 2 to the fourth, until eventually you get to your nth term. If you were to add all these up, it's equal to 1. When we reach the bottom of the slide, I will go back up and explain why this does in fact equal 1. There is a concept called partial sum where you might add just the first 2 terms, or you just add the first 3. This is denoted with a capital S and a subscript of a numerical value. S sub 1, that's just the first term. That's going to be 1/2. S sub 2 is the sum of the first 2 terms, so that's a half plus a fourth, that's 3/4. S sub 3, that is the sum of the first 3 terms of the series, a half, a fourth, and a 1/8. That adds up to 7/8. And then finally, S sub 4 is the sum of the first 4 terms, half plus fourth plus eighth plus 16th, grand total 15/16. So if your partial sum, your nth term of your partial sums, is defined as the sum of the first n terms of your sequence, then the sequence of partial sums is convergent and has a limit of s. If that's finite, then your infinite series adds up to that finite limit value, and we call it convergent. If the sequence of partial sums is divergent, then the infinite series is divergent. One special type of series is a geometric series. That's where you have a constant value, and each term afterwards progresses by some ratio with ascending powers. The infinite series, the sum from 1 to infinity of a times that ratio to the n minus 1 power, is convergent and has a sum of a over 1 minus r if that ratio, or r value, has an absolute value less than 1. Otherwise, the series is divergent. Okay, so let's go back up here and look at that series in the very beginning at the top of the slide where I claimed that there was a sum of 1. 1 over 2 to the n can be written as 1 times 1/2 to the n power. 1 to the n power, as long as they're positive integers, is going to be equal to 1. So what does that do for us? That sets us up pretty nicely. I'm going to rewrite this as I'm going to borrow a half. 1 times a half is a half. And then I'm going to leave the rest of those halves group together. 1/2 times 1/2 to the n minus 1 is 1/2 to the n. So I haven't gained, I haven't lost. What I have done is, when you look down here at the bottom, the formula, the infinite series from 1 to infinity of a times r to the n minus 1, back up here I've created that same look. 1/2 is a, r is 1/2 as well, and I've made it look like n minus 1. So I have recreated this format using 1 over 2 to the n. I wrote this as 1 times 1/2 to the n, and then I borrowed one of the 1/2s and left it one short. So a is a half, r is a half. The r value being 1/2, its absolute value is still a half. That's less than 1, and that tells us that this infinite sum or series will converge. Now here's how you find out the sum of it. A divided by 1 minus r, that's going to be 1/2 minus, 1/2 over 1 minus 1/2. Well, that's a half divided by a half, which is 1. And that's how I knew that that would add up to 1. If you are lucky enough to know the nth term of your partial sums, for this example, we're given that the nth term of the partial sums is 2n over 3n plus 5. The sum of the series is the limit of that nth term of the partial sums. Now back on the first slide, we found the sum of that infinite series through the geometric series formula. I didn't use the partial sums. Back on that first slide, if you were to come up with the nth term for the partial sums, then S sub n would be 2 to the n minus 1, 2 to the n, and then minus 1. You wouldn't put the minus 1 in the power, over 2 to the n. Now that would have a limit of 1 as well when you applied to n goes to infinity. So anyway, back to this problem. If you're given the nth term of the partial sums, then the sum of that series is the limit of that n term. For example, if we take the sum from 1 to infinity of a sub n, that's going to be the same as the limit as n goes to infinity of the nth partial sum term, which was given 2n over 3n plus 5. Remember, as n gets large, if these dominant powers are the same, you take the leading coefficient. So 2/3 would be the sum of that series, if this is the nth term of the partial sums. Now let's go back to the geometric series formula, where if the ratio has an absolute value less than 1, you have a convergent geometric series, otherwise divergent. This time we're given a series of terms, 5 minus 10/3 plus 20 over 9 minus 40 over 27 plus ... It would continue with this certain pattern. Our first term is 5. That's your a value. The ratio at which each term is continued, for example, is a ratio of -2/3. Now here's how you can figure that out. 5 times -2/3 is -10/3, times -2/3 is positive 20 over 9, times -2/3 is -40 over 27. And if you had to get the next term, you would multiply this by -2/3 again. You would end up with 80 over 81. 80 over 81. You keep multiplying. This is the rate at which your terms change. So the rate is multiply by negative 2/3, you get your next term. The absolute value of negative 2/3 is positive 2/3, so we have a convergent series. Our first term is 5. The rate at which the terms change is negative 2/3. So we have written this in the a r to the n minus 1 format. Since this converges, our sum will be 5, that's a over 1 minus r, so 5 over 1 minus negative 2/3. Well, that's 1 plus 2/3, which is 5/3. 5 divided by 5/3 is 3. So that would be the sum of this geometric series. Is this infinite series, the next example, is it convergent or divergent? It is almost impossible to tell just by looking at it, but let's write this as a geometric series. I'm going to take 2 to the 2n times 3 to the 1 minus n, and using your exponent properties, we can write 2 to the 2n as 4 to the n. 3 to the 1 minus n is 3 to the 1 divided by 3 to the n. Now what has happened here is I'm going to rearrange this. I've got a 3. 4/3 to the n, like the trick I used on the previous slide, since this is 4/3 to the n power, I'm going to borrow a 4/3 and leave it 1 short. 3 times 4/3 is 4, because those 3's will cancel. So we have 4 times 4/3 to the n minus 1. Now, if I try to add all these terms up, my a value is 4. The r value is 4/3. Now, the absolute value of 4/3 is greater than 1, so that means we have a divergent series. And that simply means that this will not add up to a finite value. A r n minus 1. If you can write a series in that format, you have a geometric series, and that ratio, if it's not less than 1, when you take the absolute value, it diverges. There's a special type of series called a telescoping series, and we use partial fraction decomposition. That's a skill that we learned back in Unit 2 to rewrite this as two fractions that are either added or subtracted together. So we're going to take 1 over n times n plus 1. That's already a factor denominator, so we have a fraction with n, a fraction with n plus 1. Remember how we would do it back then? We would put an a in the numerator for one of them, a b in the numerator for the other. These are distinct linear. Solving for a, you would get 1. Solving for b, you would get negative 1. Back in Unit 2, we would integrate. In the telescoping series, we're just taking this long enough to create a partial sum n term. So that's going to be the sum from 1 to n, whatever number we decide to stop adding. And we're going to write that as 1 over I minus 1 over I plus 1. This will be the place where the 1 gets subbed in. Then you would add and move up to a 2. So let's expand that. Plugging in a 1, we have 1 minus 1/2. That's that first group of parentheses. Plus, then your index moves to 2. So you'd have 1/2 minus 1/3. Move your index up to 3, 1/3 minus 1/4. Dot, dot, dot. When you reach the n term, you have 1 over n minus 1 over n plus 1. The term before this, see how these progress? It's 1 minus half, and then you have half minus a third, third minus a fourth, and so forth. The term before the last one would look like 1 over n minus 1 minus 1 over n, and then we would plus, and then we'd have that last set of parentheses. When you go through here, and I'm going to switch color to blue, that's a nice gentle color. That half and that half cancel. Your thirds cancel. See how one of them's negative, the other one's positive? This negative 1/4 would cancel. Your next term would have been 1/4 minus 1/5. See how this works? It telescopes out. But that 1/4 would have canceled that one. Dot, 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 you get towards the end, that one cancels that one. So ultimately, you're left with that term and this term. All the ones in between will cancel each out because they have a positive and a negative partner, and they'll cancel. So what does that leave us? That tells us that our partial sum n term is 1 minus 1 over n plus 1. As we let the n values go larger and larger, this term goes to 0, and that leaves us with a 1. That's a finite number, and if the limit of the partial sums is finite, this infinite series will converge and have a sum of 1. There's a couple theorems. If your infinite series is convergent, then the limit of your a sub n term is 0. This is not a two-way street, though. Just because a limit is equal to 0 doesn't mean it's convergent. So you have to be careful there. Only read these one way. If your infinite series is convergent, the limit of a sub n is 0. Now, there's something that, if you had discrete math, it's called a contrapositive. If you read the theorem backwards, you have to negate the front and the back. For example, starting in the back, if the limit as n approaches infinity of a sub n is not 0, then the infinite series a sub n is not convergent, it's divergent. So if a theorem is written in one direction, logically you can negate the end and call that your if, then that. But both will have to be negated. This one's called the divergence test theorem. It's very handy. You can take a quick limit if it's not 0, or if it's not defined, then your series is divergent and it won't have a specific sum. This one, the example underneath, show that the infinite series of n squared over 5n squared plus 4 diverges using the divergence theorem, which is this one. If we take the limit as n goes to infinity of n squared over 5n squared plus 4, the n squareds are matching as far as power is concerned. That means our limit will be 1/5. You take the lead coefficients as long as your powers are the same. So that's 1/5. And guess what? That's not 0. So the first part of this theorem is met. The limit of our term, nth term, n term, is not 0. Then a sub n is divergent. The bottom two examples I have done on another slide, on another video, so I'm going to bypass that. But I did want to quickly mention that the divergence theorem is very handy. When you see a term and you're in an infinite series, if you see an n term, this would be your a sub n. If you do a quick limit as n goes to infinity, if that doesn't equal 0 or it doesn't exist, then you can go ahead and say that your infinite series diverges. I hope this video has helped. It's a lot of information real quick. Let me know if you need anything. Reach out by phone, email, stop by the office or ask in class, and I'll do my best to help you out.